let's now get into determination of empirical and true formulas. Remember, we have two ideas. We have the true or the actual formula, which is the actual representation of number of elements making up a molecule. And then we have the empirical formula, which is the simplest, or the simplest version of the true formula. So you could have, sugar as C6H12O6. So this could be the true formula. And then we have the representation of CH2O. And then this would be the empirical. Right, where we've reduced all the values by 2. We've got now the simplest version of that formula. So that's the deal with the true and the empirical. As far as the definitions, we've actually already covered that. And so the empirical formula is, it is basically determined through experimentation. And we can look at this in terms of, elemental analysis or combustion analysis. So, and that's kind of the old school way. We still use it a lot, even to this date, but, it's really just to derive the simplest version of one element to another within a molecule. For the true formula, we need something more. We basically need a molar mass to create basically the true formula from the empirical. We often use mass spectroscopy to basically determine the true molar mass for a molecule. So we have these two different aspects, but obviously they're both related to one another. Old school chemistry, we tend to do the empirical route first, and we still, like I said, do that today, even in research. Getting elemental analysis or combustion analysis is still widely used in conjunction with then mass spectroscopy to then make the connection between the empirical and the true molecule or molecular formula that that you've created as far as this new molecule made synthetically or what have you. So let's look at some examples of determining empirical formula first. And then we'll get into determining basically both of them. So as far as determining empirical formula, we have, I guess, a couple of different ways to determine that. One would be basically, based off mass of elements in the molecule. Second type of version we would see would be based off, kind of the same idea, but mass percent of elements in the molecule. And then the third one would be, based off of mass of products, in a chemical reaction. So those are the three ways that we can determine empirical formulas. To determine, the true, you need, basically a molecular molar mass given. If you take the empirical molar mass and, apologize, that should be on the denominator side of things. You take the empirical molar mass and divide it into the true molar mass, you basically get a ratio. And if you take then the empirical formula times that ratio, now you actually have the true formula. So the second half, the true formula, is always the same. It's really the first bit, the empirical formula determination. It's usually the tougher part of the piece, piece of the question. So let's go through an example of each one of these three that we just discussed. Okay, so here's our question. We have, chemical analysis of a copper chloride found that a 2-gram sample contained 0.945 grams of copper and 1.055 grams of chlorine. What is the formula for the copper chloride? So, we have a couple of different pieces of information that are going to help us here. We have this mass of our copper. We have mass of this chlorine. And ultimately, we're talking about a copper chloride. So, we have this 2-gram sample, but really it's just kind of describing whether we have something that's kind of pure or not. Meaning that, if we look at the 2-gram sample, well, that is really the combination of those two constituents. So, this basically makes up the sample. So how do I look at solving this type of question as far as the copper chloride, formula? It's all about moles, right? What we want is copper and how many moles copper has, and then chlorine and how many moles chlorine has, and then relate those two actually to one another. So the first step that we have here is really just getting to moles of both of these entities. So if I have 0.945 grams of copper, and copper has a molar mass of 63.5 grams per mole, right, I have then 0.01488 moles of the copper. So getting out of grams and getting into moles. And then I do the same thing with my 1.055 grams of the chlorine, where I would be dividing that by 35.5 grams per mole to get a value of 0.0297 moles of chlorine. So this is what now allows us to develop the formula. And that's really step 2. Now we know we have copper. Well, we have 0.01488 moles of that copper. And we have chlorine, which is 0.0297 moles of chlorine. We can't have fractions, or decimals. Of elements in a formula. So basically we divide by the smallest mole value to, simplify and develop the ratio. So if we take the copper, we have the chlorine, right, we will be dividing by the smaller of the two values. This is 0.01488. And when we do that, we get copper 1 Cl2, or our formula is copper Cl2 or cuprous chloride, or our copper 2 chloride. So that's one way to develop an empirical formula, is through mass of the elements that actually make up the formula. The second example of this would be looking at mass percent. So we're going to find is very similar to this process that we just discussed. It's just the beginning that, we have to do a subtle, a subtle change to. So it was determined that a poisonous substance contained 58.77% carbon, 13.81% hydrogen, and 27.40% nitrogen by mass. What is the empirical formula for the poison? And if its molar mass was determined to be 306 grams per mole, then what is its true formula? Okay, so now adding a little bit more to the question, right? Here, in terms of kind of breaking things down, first we want to know what the empirical formula is. And so we can think about that as one. What is the empirical formula? Here, looking at carbon moles and hydrogen moles and nitrogen moles. And so that's kind of, the first bill. And then we have, the second bill, which will be then what is the true formula. If we know its molar mass is 306 grams per mole. So we have really two pieces to this question. First the empirical, and then next the actual true formula. So step one, basically we're going to use the mass percents to get to mass of each element in the molecule. And then moles, right? And that's really what we want to get into, right? We want to get into that mole game to develop the empirical formula. And with mass percents, if you basically assume your sample is 100 grams, well, then all the mass percents turn into mass. So it's a real quick way to kind of just, get through that mass percent idea. So if we go back up to the top, here are those mass percents that we were looking at. So we had, 58.77% in terms of our carbon. We then had 13.81% of that hydrogen, and then we had 27.40% of the nitrogen. So we're immediately just, jumping off and saying, okay, well, that means we have 58.77 grams of carbon with that first assumption. And now I'm just dividing by my molar mass to get 4.90 moles of the carbon, right? So just that quick conversion. And now we're doing the same thing with the others, with their 13.81 grams of hydrogen. So that gives us 13.81 moles of hydrogen with that conversion. And then with the nitrogen, we have our 27.4 grams dividing by the 14 grams per mole of that monoatomic nitrogen to give us 1.96 moles of the nitrogen. So here is how we develop, right? That's where we now develop, our empirical. So we would have our carbon with our 4.9, our hydrogen with our 13.81, and our nitrogen with our 1.96. So we want to divide by the smallest and simplify the process. So we would have really a division by the nitrogen. And if we do that, we end up with carbon at 2.5, hydrogen at 7.0, and nitrogen at 1. We can't leave a fraction. So, you got to get rid of it. And that's pretty simple to do. If we multiply through by 2, that gets rid of that fraction. And so there is our first part of the question. What is the empirical formula for this poison? So same idea as before. We got to get to moles of each one of the elements. Once we get to moles of the elements, we can then start to develop the ratio, develop the relationship between one element and another within the molecule, and then develop the empirical formula. The second part was then, right, what's the true formula? We know the molar mass, but we don't know what the actual true formula is. So if we go back to the empirical, right, which we have above, the empirical molar mass for this molecule is 102 grams per mole. So I want to set up that ratio of, the empirical molar mass and the true molar mass. So we have our true molar mass of 306. We have our empirical of 102. And the ratio is basically 3 to 1. So now we just need to take that empirical multiply it by the ratio, and that gives me the true formula. So I'm looking at the C 5, H14, and 2. I'm multiplying it by 3 to give me C15, H42, and 6 as now the true formula for that process. And so that's how we can now go that extra step to the actual true formula. The third version that we can see with this type of empirical formula determination is with a chemical reaction. So let's look at this example. Okay, so here's our question. We have, a sample of mothballs. To be honest, that takes me back to my grandmother. Used to like the smell of that in our closet. But sample of mothballs, which has a formula of CXHYClZ. So basically saying it's a molecule made of carbon, hydrogen, and chlorine. And this is combusted. When it's combusted, it produces products, and our products are 0.543 grams of carbon dioxide, 0.074 grams of water, and 0.1458 grams of chlorine gas. Those are all produced. The true molar mass for the molecule was determined to be 147 grams per mole. And knowing that, we should be able to determine the true formula for our mothballs. So here's our reaction. And so here are the mothballs. It's the molecule that makes those up. And we have certain masses of these products that are actually produced according to that combustion process. So somehow we have to be able to develop that, empirical formula in terms of, we got to be able to determine moles of carbon, moles of hydrogen, and moles of chlorine. But how do we do that now that we, have this new representation as far as a chemical reaction is concerned? And so we have to remember, Dalton's, atomic theory. Right, this idea that, elements are indestructible elements do not turn into different elements in a chemical reaction. So that means if we look at, like, in the sense of, here we have starting materials above, and those starting materials are going to produce products, that the moles of carbon that is produced is equal to the moles of carbon that you started with. Or, another way to really say that is moles of carbon on the starting material side have to equal moles of carbon on the product side. And the same goes for, all the elements. Like we have here with, hydrogen and chlorine, oxygen, right, etc. So we can get at essentially moles of carbon from moles of CO2. We can get at moles of hydrogen from moles of H2O, and we get at moles of our chlorine from moles of the chlorine gas. So that's just now the relationship. We're just taking the molecule, relating it to moles of a particular element within the molecule, and then taking that moles of the element and then relating it to a different molecule within a chemical reaction. So we would just look at this kind of mass conversion to begin with, saying that, well, I started with, or produced rather, 0.543 grams of CO2. If I divide by my molar mass of 44 grams per mole, I get into moles of CO2, and then using the formula, I can get to moles of my carbon, which is 0.01234 moles of carbon. And now I just repeat that process for the other two. I have 0.074 grams of my H2O, dividing that by 18 grams per mole. That gives me into moles of my H2O, and then for every 1 mole of H2O, there's 2 moles of hydrogen, and so that gives me 0.0082 moles of my hydrogen. And then lastly, we finish it off with the chlorine, the 0.1458 grams of the Cl2, right? We're dividing that by 71 grams per mole. And then for every 1 mole of Cl2, we get 2 moles of that monoatomic chlorine. And so that gives us a mole value of 0.0041 moles of our chlorine. So that's helping us to develop that formula, right? We have our 0.01234 moles of our carbon, 0.0082 moles of the actual hydrogen, and then 0.0041 moles of my chlorine, or I guess we should say our chlorine. So now we're simplifying that process, right? So we wanted to divide really by the, the chlorine in this case. And when we do that, we get a formula C3H2Cl. That is our empirical formula, and that has a molar mass of 73.5 grams per mole. We're not done yet, but we have to get to that point, right, of developing the empirical. And so now, if we take our true, divide it by the empirical to get to that ratio, right, we would have 147 grams per mole divided by 73.5, and we get a ratio of 2 to 1. So we would take that empirical formula, multiply it by 2, and here is our true formula now determined. So that is the third and final example of developing formula from empirical to true formulas, and that's definitely the gambit as far as examples that you will see.